Hello class. In this video we're going to take a look at an inference procedure called a two-sample t-interval, which is used to estimate a difference in a certain mean between two independent populations. So it's going to follow a lot of the same types of things that we learned in the other confidence intervals that we've covered. And this one we're going to have a new formula, and let me see if I can share these. Where did it go? There we go. All right, so we're going to see a couple new formulas here, but a lot of the things that we're going to cover in this video are really just things we've learned that we're applying in new ways. So the two-sample t-interval is used to estimate the difference in a population mean for two independent populations. For example, do Japanese cars get significantly higher gas mileage on average compared to American cars? That would be comparing the difference between a mean for two different populations, Japanese cars, American cars. How many more or less hours do women sleep compared to men on average? It's comparing two, or an average between two populations. What is the average difference in AP exam scores between juniors and seniors? How much more expensive is an apartment in New York City compared to a similar apartment in Chicago? These are all questions that we can answer with a two-sampled t-interval, because they're all about comparing a mean between two separate populations. In a two-sample t-interval, there are the same three basic condition checks that we've been using for all inference procedures. Number one, both samples need to be randomly selected, or in an experiment, subjects are randomly assigned to their treatment groups. That helps limit bias and helps ensure that the sampling distribution has a mean equal to the parameter of interest. Number two is that the sampling distribution has to be approximately normal for each sample. And this could be met in three different ways. The first way is that the population distribution is just already known to be normal. It's stated in the problem. If that is not known to be true, then hopefully we have sample sizes that are large enough to use central limit theorem, so samples of at least 30. In this case, since there's two samples, both samples would need to be at least 30. And if that's not the case, or if one of the samples at least is not at least 30, then we need to look at a graph of the distribution of the data to see that it's roughly symmetric with no outliers. We only, again, need to do this check when the sample size is less than 30. And number three is that the samples need to be independent. And if we're sampling without replacement, then the population has to be at least 10 times the sample size for each sample. Now, this might sound pretty similar to a paired table, because that involved two kind of sets of data, and we looked at the difference between the measurements. But what's different here is that in a paired t-interval, the subjects in the study have to be paired up, or we're taking two measurements on each subject. Think of it this way. If you were to take the measurements you had, you've got measurements for this person, measurements for this person, or two measurements on the same person. If you shuffled those measurements or shuffled the data, it would ruin it. It would break up those pairs, and it would totally defeat the purpose of pairing them up in the first place. So in a paired t-interval, shuffling up that data would ruin it. Would break up those pairs. Another thing to look for is that in a paired t-interval, the differences are calculated on the individual level. So we would look at these two people paired up as individuals. How different were those people? In a two-sample t-interval, the individual measurements aren't paired up in any way. So we don't have a person from this sample paired up against a person in that sample, and we look at them together. Shuffling those individuals around wouldn't affect anything because they weren't paired in the first place. Another way to think about it is that the difference estimated is on the population level. So we're not looking at the difference between individuals, we're looking at the difference between the populations overall. All right, so here's the formulas that we'll need to know. The standard error of a two-sample t-interval is the square root of s1 squared over n1 plus s2 squared over n2. It's really the sum, it's the squared sum of the individual standard deviations that we would have. So standard deviation from the sample 1 squared over sample size 1 plus standard deviation 2 squared over sample size 2. and that whole thing in the square root. The confidence interval formula is going to follow the same structure of all the other confidence intervals we had. It's the estimate plus or minus your critical value times your standard error or standard deviation of the statistic. Well, the estimate is your estimated difference. So mean 1 minus mean 2. Your sample mean 1 minus sample mean 2. The critical value is the number of standard deviations you'd go to capture the percentage that matches your confidence level. And that's T star. You're going to find that on the table. And the standard error is this formula up here, square root S1 squared over N1 plus S2 squared over N2. One extra detail that you need to know about when we're dealing with means in a t-interval is that we need to deal with degrees of freedom. Now, in the past, we've seen that degrees of freedom is the sample size minus 1, and when you're dealing with just one sample, that's how it's going to be. But if you're dealing with two different samples, it's a little more complicated. So I want to break it down into the two ways you might be finding your interval. If you're constructing the interval on an inspire, using the function on the inspire, I'll show you that in a little bit, then that function is going to calculate the degrees of freedom for you. You don't even have to think about it at all. Just put in your info, it'll give you your degrees of freedom. Just make a note of it as part of your answer. Now, if you're constructing the interval by hand and finding T star on the table, you should use the degrees of freedom from the smaller sample. That errs on the side of caution. So if you have one sample that is 30 and one sample that's 20, you would use 19 degrees of freedom because your smaller sample is 20. And remember that if you're looking on the table and your degrees of freedom is not listed, to round down to the next lowest. You'd never round your degrees of freedom up because that would act as if you had more information than you really have. All right, so let's take a look at an example. So in this example, how much more money do New York renters pay for a one-bedroom apartment compared to Chicago renters? A random sample of 50 one-bedroom apartments in New York has a mean monthly rent of $2,900 with a standard deviation of $425. A random sample of 50 one-bedroom apartments in Chicago has a mean monthly rent of $1,800 with a standard deviation of $360. First thing we'll do is just calculate the standard error of the average difference in monthly rent. So the important piece of information here are the mean from one sample. So the mean in New York is 2,900. Standard deviation in New York, 425. And the Chicago sample had a mean of 1,800 with a standard deviation of 360. Now we could use subscripts of 1 and 2, but I like to be a little more descriptive. And so I'm saying X bar NY and SNY, those measures are for New York. And X bar CHI, SCHI, those are for Chicago. All right, so we're going to take our standard error formula, square root of S1 squared over N1 plus S2 squared over N2, substitute what we know. Standard deviation for New York was 425, so 425 squared over 50, because there were 50 apartments sampled from New York, plus standard deviation in Chicago was 360 over 50, because there were 50 apartments sampled from Chicago. Altogether, that's going to give you a standard error of 78.77 or $78.77. Now, that does not mean that that's the difference in, or the estimated difference in rent. That is how much our differences will vary. So to interpret this, I might say something like, in many samples like these, the average differences in rent will vary from the true difference by about 78.77. So if we took another sample of 50 from each city, we might see that our differences found on average the average differences would deviate by about 78.77. All right, well, let's take a look at constructing and interpreting the confidence interval. So the full 4-step process. So same example, but here the instructions are different. Calculate and interpret a 95% confidence interval. In step 1, we're going to state what we're going to do. We will estimate mu NY minus mu CHI. So that's the mean, or that's the difference in the mean monthly rate for the New York one-bedroom apartments and Chicago one-bedroom apartments. And we're subtracting in this order New York minus Chicago. So if we get a positive number, we know that means that New York is more expensive on average. Negative numbers imply that Chicago apartments are more expensive on average. In step 2, we're going to plan what we're going to do. So we will construct a 2-sample t-interval with a 95% confidence level if the conditions are met. Condition 1 is that both samples are randomly selected, and that is stated in the problem, random sample of 50, random sample of 50. So we're good on the random samples. For the large counts, both of the samples are at least 30. We got 50 apartments from New York, 50 apartments from Chicago. So since those are at least 30, the central limit theorem applies. And finally, our samples are assumed to be independent, and there are more than 500 one-bedroom apartments in each city. We're assuming that that is true. All right, in step 3, we will calculate. And I'm going to show this calculation by hand using t star we would find on this table. So our sample sizes are both 50. That means our degrees of freedom from one sample is 49. That's what we're going to use. So we're going to use this formula setup, x bar 1 minus x bar 2 plus or minus t star times that standard error. All right, well, let's see. X bar 1 is 2,900. X bar 2 is 1,800. T star, we're going to get that off of the table. So if you look in your table at the bottom, find your confidence level 95%, and then follow that up to your degrees of freedom. 49 is not listed on the table, so we're going to round that down to 40, and 2.021, that's our value of t star that's going in here. That's our critical value. Times our standard error, 425 squared over 50, plus 360 squared over 50. If you calculate this difference, well, it looks like the average difference was in New York is $100 more, or $1,100 more, and the margin of error is 159.19. So our estimates, it says that we believe that the one-bedroom apartments in New York are about $1,100 more expensive than Chicago, and that varies by, we have about a $160 margin of error. Our final confidence interval, if you add or subtract that margin of error, would go from 940.81 to 1259.19. So let's go ahead and interpret that in the next step. And so we would say that we are 95% confident that the true difference in mean rent for one-bedroom apartments in New York City and Chicago falls between 940.81 and 1,259.19. And what that means essentially is that one-bedroom apartment in New York City is expected or is likely to cost about 940.81 to 1259.19 more per month than a one-bedroom apartment in Chicago. So let's take a look at how to run this interval on the Inspire. All right, so on the Inspire, go ahead and open up a calculator page. So we'll go to page 1. And then we're going to hit Menu, 6 for statistics. Let's see, 6 for confidence intervals. And we're looking at number 4, a 2-sample t-interval. First thing it's going to ask you is, what's your data input method? We would choose data if we had 2 lists of all of the individual rent for those 50 apartments from each city, but we don't have that. We have the stats because it told us the summary statistics. So we're going to choose stats and hit OK. X bar 1, let's see, the rent in New York City was 2,900. Standard deviation was 425. Rent in Chicago was 1,800 on, nope, that's our sample size. What am I doing? 50 is our sample size. Average rent for Chicago was 1,800. Standard deviation of 360, and the sample size there was 50 as well. I like to hit the tab button because there's some things that aren't listed on here. So if you hit tab, it'll go to the next one, our confidence level 0.95. And then it'll ask you pooled, and just always say no. Say no if it asks you to pool. That's a separate thing. We're not going to get into that. So just say no to pooling. Everything is all set. We're going to hit OK. And here's what we have. X bar diff is our estimated difference. There's a margin of error. Go up a little bit. There's our C lower and C upper. So there's the boundaries of your confidence interval. So make sure you list those out. They're going to be just a bit different than what we calculated by hand because we have a more exact measure for degrees of freedom on the calculator. We used 49 degrees of freedom. Actually, we calculated with 40 degrees of freedom. But on here, the exact degrees of freedom is 95.4187. So that's the exact degrees of freedom. Either way you do it, just make sure you specify, here's the boundaries of my interval, and here were the degrees of freedom that I used. If you have those things in step 3, then you're good. You don't need to show any additional work. All right, so from this video, you should be able to work through the process of running a 2-sample t-interval to estimate the difference in population mean between 2 independent populations. In the next video, we're going to take a look at the 2-sample t-test, which tests for a significant difference, more of a yes or no answer on, are these significantly different, whereas an interval is how different is the mean for these 2 populations.